Let us start this lecture with a thought process that modern education system may provide ways and means to get a living, but it takes you away from the rainbow of life. Even today it is not giving you the job. So now earlier in the last lecture, if you look at, we are discussing about various temperature like a dry bulb temperature, wet bulb temperature, adiabatic saturation temperatures and other things, and we learned that how it can be related to the relative humidity and specific humidity. And we will look at this, all these properties can be put into a chart which is known as psychometric chart, and that is very helpful for doing the calculation easily. And as we have seen that it is quite cumbersome to calculate all the things. Of course, nowadays the computers are there and then you can do all those calculations very easily, but earlier days there was not such kind of provision was there. So therefore, people devise a psychometric chart to carry out the calculations. They devise a psychometric chart so that it can be utilized very easily in the subflow, right? And of course, they will do all the calculations and put into that, into the picture. So the typical psychometric chart is shown here. If you look at that here on this, you can say that horizontally it is shown, that is TB. This is a dry bulb temperature, 0, 10 degrees Celsius, 20 degree, 30 degree, 40 degree, right? And in the vertical line, this is of course along the horizontal line, the dry bulb temperature is shown, and the vertical line here it is shown the specific humidity, that is kg of water per kg of air, right? And this line, if you look at, this is basically giving me the wet bulb temperature, right, which is also this line corresponding to the RH is equal to 1, that is the relative humidity, right? And keep in mind that, and this relative humidity is parallel to this line. Let us say this is a 100% relative humidity 1, and relative humidity 0.8 it is given here, and relative humidity 0.6 and 0.4, 0.2 it will be given, right? And this scale shows the enthalpy of the moisture, that is kilojoule per kg of dry air, right? That gives the enthalpy. And also the specific volumes and other things will be giving. Let me just show you, this is just to illustrate this point, these are all given together in a plot, and that we call it as a psychometric chart. And if you look at, it is the same curve, but only I am just giving little illustration, here, that if you look at these lines, blue lines, relatively 10%, this is 20%, this is 30%, and goes on until this ends. This is basically 100%, right, relative humidity. And these lines, right, green lines, if you look at, it is basically the specific volume, and this line, red line, is the enthalpy line, like 98 kilojoule per kg, 75 kilojoule per kg kind of thing. And these temperatures, 5 degrees Celsius, 10 degrees Celsius, 50 degrees Celsius, all those temperature is basically the wet bulb temperatures, right? See, this looks to be very clean and clear, but I will tell you the actual diagram is quite complex. I will show you that. See, this looks like, are you getting? Okay, I have gone through it little slowly so that you will have feel. Now, so if you look at, that is dry bulb temperature in the horizontal line, this is your dry bulb temperatures, right? This point like 0 degrees Celsius, 10 degrees Celsius, 20 degree, like that. And here this point, this line is basically gives me specific humidity, right? These 2, there will be 4, 6, 8, 10, 12, like all those things. That is a gram of moisture per kg of dry air. This is in grams, right? Okay? Are you getting? These are, like 2 gram, 4 gram, 6 gram, 30 grams like that. As I was telling, this line, that is earlier it was a green line, like this line is basically volumetric, volume, specific volume per kg of dry air, the water vapor volume, right, per dry air. And this dashed line, if you look at this dashed line, are basically wet bulb temperatures, like, if you look at, this is the wet bulb temperature, like in this case is 25, in this case is 30, and then it goes 20 and like that, like 5, 15, 10, 5, 0. And these lines, it gives me enthalpy of the moist mixture, kilojoule per kg of dry air, right? And what else is there in this? The one very important point is the relative humidity. This line, you see, if you look at this line, is basically 10%, 20%, this line, right? These lines are basically relative humidity points, right? Okay. So if you look at it, contains a lot of data in one plot, and that we call it psychometric chart at 1 atmosphere pressure, right? If you want a different thing, it will be different, right? For example, when you are going for a higher altitude, the pressure will be lower, then you will have different values, little bit changes. So now, if you recall that we had taken a temperature, like what you call dry bulb temperature, right? And we also looked at the wet bulb temperature as 30 degrees Celsius, right? And we can solve this problem, what we had done by calculating and considering it as an adiabatic saturator, right? Or kind of things, that we can do very easily here. Because we have done a lot of calculation, but here we can do very easily. What I'll do, I know this dry bulb temperature, that is 40 degrees. That means I'll have to go through this one, right? This point. What I'll have to go through? I'll have to go for this 30 degree. Wet bulb temperature is what? This is your wet bulb temperature. Which one? This dashed line. The solid line is corresponding to the enthalpy. Okay? The dashed line corresponding to that means it will be crossing here. Are you getting? That is the point. Please be careful and look at again. Like this is my wet bulb temperature. I do a vertical line. This is my vertical line. Right? And my temperature, wet bulb temperature is 30 degrees, this dashed line. It is coming and crossing here. So what will be my relative humidity here? What will be? My relative humidity, this is 40 and this is what? 50? This line is 50 or not? This is 50, relative humidity. And this line is 40. So here it will be around, you can say 0.45. You can also do a linear scale and then interpolation, you can do that. Okay, but let us say that the relative humidity will be, in this case, relative humidity is RH1 is equal to 0.45. Earlier, how much you got? How much? It was 0.497. So that is the error. By calculation, we got 4.97. You can say it is 0.5, but here it is 0.45. There is an error in that. And then I want to have a specific humidity. What I will get? How I will get? What I will do? I will go this point. I go directly here. Right? This point. That is, this is 22. Right? This will be something 23. Right? That means I got SH1 is equal to 0.023 kg of water per kg of dry air, right? This is in grams, therefore it will be 23 grams, right? Are you getting? So earlier how much we got? How much? That we got 0.0, 0.0237, right? From calculation, this is from psychometric chart, right? Psychro, right? Chart. From calculation, we got SH1 is equal to 0.0237, right? There is an error, of course, but it is very quick. So, what is the enthalpy we got? What will be enthalpy? Enthalpy here, approximately around 100. This is your enthalpy. So, from psychometric chart, we are getting enthalpy of mixture is 100 kilojoule per kg. But here how much you got from calculation? Calculation we got the HM1 is 101.2 kilojoule per kg. So it is approximately, so quickly, because I need not to do the calculation. Are you getting the efficacy of using psychometric chart, right? Quickly you want to do something, in a subfloor or in a very complex situation, you need not to do all those calculations, right? Of course, nowadays it is very easy. You are having a program, you just give the point, press a button, it can come very easily. Okay, the situation has changed, but this still being used in the subfloor, right? So you should learn how to use this psychometric chart for solving the problem, right? Is that clear to you people, or any doubt? Can I repeat again? Okay. So as you do not need, then let me not repeat. So now just to illustrate little further, what I will say that, if you look at, this is the point. What is this point? This is your specific humidity remaining constant along this line, right? That is the parallel to your TV will give you. And this line, dashed line, is RH, relative humidity, and this line will give me enthalpy, right? And the GH, if you look at, that will give me wet bulb temperature. It is, sometimes it crosses, sometimes it goes slanting, right? It's not same as that of the relative humidity, but it is very, the wet bulb temperature is not same as that of the enthalpy, but it is very closer to that. That you should keep in mind, right? And of course, this vertical line, if I go, it will give me, dry bulb temperature. So this is the way how you can go about. So if you look at, like which we have already seen is that A star, this what I am using here, you may not get in other place, but I am using HA plus HH into HW, and of course this is corresponding to the gas vapor, right, WG. And for the adiabatic saturated, you can get all those values, like we have already discussed, and keep in mind that this, if you do that, H1 star SH2 minus SH1 into SW3, this already we have done, is equal to S2 star. So, and if you look at, this is basically a small quantities, this is quite a small quantities, right? So therefore, this is, you can neglect, and that H1 star is, is equal to S2 star, that you can say, saturated, adiabatic saturated. So therefore, A star almost coincide with the TW, you can say, right? And of course, I have already talked about the vertical line represents the dry bulb temperature, and the horizontal line represents the specific humidity. And so now what we will be discussing basically about air conditioning process. And if you look at air conditioning, why we need, not only the maintain the temperature, but also the maintain the humidity. As I told in the last lecture, that humidity plays a very important role depending on the temperature, right? So And we need to also maintain temperature and very well, because you will have to maintain your temperature, body temperature, which is maintained around 37 degrees Celsius. And if it is a summer, then what will happen? If it is 40 or 45 kind of degree, tell you what we experience, then the body cannot give out the heat. It will be uncomfortable because temperature gradient, okay. So body has to give heat to maintain the temperature, because body is like a human body or animal body, other things also, they are like a heat engine. It gives out energy, right? So in the winter, it is other way around. It will be giving more amount of heat to the atmosphere because the temperature is lower. You know that if temperature goes below 10 degrees Celsius, it is very difficult to, this to sustain, and your comfort level will be lower, right? So therefore, we need to maintain temperature, also the humidity. So we will be looking, conditioning the air for that process. Let us see that what we can do. To maintain this relative humidity and also the specific humidity, and then what you can do, you can think of doing the heating. When you are heating, right, of course the specific humidity you can think of, you can humidify it, right? You can add some water, you can dehumidify it, that means you can remove some water from the air, you can cool it, you can cool, also dehumidify, various process one can think of, and that is nothing but your air conditioning, right, what we will be discussing. So we want to analyze these air conditioning systems. What we will have to do? We will have to do our standard assumption, because this is a flow process, that is the steady flow process, and we consider one dimensional for simplicity. Actual case it will be three dimensional kind of things, but we are, for our case, we are considering one dimensional. Also the uniform flow, flow need not to be uniform in a air conditioning duct and air conditioner, right? And change in kinetic energy is 0, change in potential is 0, and we are not using any shaft work for this, but then we can consider it to be 0 shaft work. So these things we will be doing, all the cases, I need not to repeat. And then what we'll do, we'll mass balance, dry mass balance, that is for the air, summation of air mass flow rate at the inlet is equal to summation of air mass flow rate at the exit of any duct, whatever we are considering. And the water mass balance, summation of water mass flow rate at the inlet is equal to summation of mass flow rate at the exit. And we will be doing the energy balance, the summation of the enthalpy at the exit minus the summation of enthalpy at the inlet is equal to Q dot minus W. And shaft work we may neglect, most of the time we will be neglecting, but heat always will be there, so we cannot neglect. So this is, let us look at simple heating or cooling, right? Let us look at simple heating coil we are having. There is some flow rate which is entering into this duct with a temperature T1 and SH1, that is specific humidity and relative humidity, and then when you heat, there will be change in the temperature definitely, because you are heating, right? If you are heating, what will happen? Temperature will increase, right? So what will happen to the specific humidity? What will happen to the relative humidity, right? So the specific humidity will not be changing. Why? Because you are not adding any water vapor or water, right? Water vapor into the system. So therefore, specific humidity will be remaining constant. But then what happens to relative humidity? What will happen? And what will happen to the dry bulb temperature? Definitely, what will happen? Because you are adding heat. When you are adding heat, then there will be increase in temperature, right? And if you are, not adding any moisture, but you are increasing the temperature, right? So what will happen to the relative humidity? Relative humidity is the basically ratio of the water vapor divided by the maximum water vapor it can take. With the temperature, what happens to the saturated pressure? If temperature is increasing, the saturated pressure will be what? Increasing, right? Yes or no? If it will increase, then what happened to relative humidity? Relative humidity will be lower, right? So if you look at the process, you are here and you are heating it. So therefore, what will happen? That it will go through this process here, state 2, and TB is higher. This TB, dB, right, is greater than the TdB1. Yes or no? Right? Because you are heating. And then relative humidity gets reduced. Right? And you can do this analysis. The mass is conserved, right, for this process, mass of dry air, right? And water also is conserved because you are not adding anything. And if you do energy balance, that is in this equation, right? If you do, there is no shaft work here. So therefore, m dot A1 S2 minus m dot H1, because you are not adding any water. So therefore, only air will be there, is equal to Q dot. And if you divide by this m dot A here, m dot A here, this will 1, and that is nothing but your Q. So S2 minus H1 is equal to Q, right? As a result, the TdB at the station 2 will increase, and relative humidity is increased. Let us say that RS2 is equal to, let us say 20%, and let us say this is your 70% kind of thing. That means 70 to 20% it has gone. If it is, the relative humidity is very low, what will happen? In the winter season, let us say you are using a heater, the relative humidity is lower. So what problem will face? Your skin will be dry, right? And some people may get, like what you call jittery kind of things, right? So if it is dry, you may be getting itching and other problems, so then you cannot. So now what is the way out? Of course, you can get the similar problem, some other opposite of that whenever you are cooling. Suppose cooling means I will be giving the cooling here, so that if you are at station 2, you will be going towards the station 1, then there will be increase in the relative humidity. See, if it is relative increase and temperature is very low, so what will happen? You will be also uncomfortable, right? So you go both the side, you will be having problem. So you will have to look at it. What we do? Therefore, in the winter season, when you use the heater in your room, you will find dry skin you are getting more, right? That means you will have to humidify it. That means you add some water moisture so that you will not face that problem. So as I told that one has to humidify the heated air to have desired value of relative humidity for better comfortable environment. And let us say heating with humidification, we can do that. Like you can think of adding, this is the heating coil, and then you can add some steam and some spray kind of thing you can use, right? And so that it can moisture. Like what will happen? 1 to 2 you are heating, that means specific humidity is remaining constant. And from 2 to 3, what will happen? Like you will be adding some moisture, so the moisture content is increasing, right? And then the specific humidity increase. Also what will happen to relative humidity? Relative humidity also will increase, because this is a lower curve and this is higher, so relative humidity will increase, so that you will be more comfortable, and dryness and other things problem, whatever you will be having. So this is known as these things like heating with humidification. So if the relative humidity is quite high, right, as I told, like if you are cooling it, right, you are in 20%, you will go to 70%, or you may go to 90%, right. So what will happen? How can we reduce that? It's a very simple answer that I already told you, that we can dehumidify air by cooling the air below its dew point temperature, right. So you can think of using the cooling coil here, and this will be low temperature and it will be a high temperature. then what will happen? You will go from, you are here, right? You are here, and then when you cool it, so you will come to this point, that is your wet bulb temperature, right? Dew point. So that after that what happened? It will be 100%, relative humidity will be 100% at this point. So then it will be started deeping in, like if you look at, there will be some moisture we can collect over here, these are all moistures which are condensed, condensing. Moistures which are condensed are coming as a droplets, and then you can collect it, right? You can collect that one, and then as a result the moist air which is coming over here, it cooled, and then you will get over here. Then now here also the relative humidity temperature is lowered down, right? dB has come down here. In this point dB is what you call, dB3 is very less than the dB1, right? But however, the relative humidity is 100%. So you have not solved the problem. So if I want to get, something lower relative humidity which is comfortable, what I will have to do? What I will have to do? I will have to again heat it, right? Again heat it. If I heat it, then what will happen? It will go this way, right? Because specific humidity is remaining constant, then I can get this is your relative humidity, right, which is, if I take this point 4, that 4 will be less than RH3, okay, and of course this RH4 is greater than the RH1. That is the one way of solving the problem. But there is another way of solving the problem, that you mix some other air, right, which is having different relative humidity and relative specific humidity will mix, then you can get this thing. So therefore, we can think of using that, which is this mixing of the different moist air and different temperature and different kind of things is being used routinely in air conditioning applications, right. So we will be looking at the adiabatic mixing of air streams, right, okay. So in this case, particularly this is being used for large rooms like hospital, like this auditorium, like lecture halls, community halls, kind of things where you need to mix the air and then allow so that people can have a comfortable zone. So therefore, let us look at a typical case. Will be looking like that, like there is one stream is coming with SH of 1 and some enthalpy, right, of course at certain temperature, and then similarly there is another stream which is entering into this tube, right, this is your tube, and with the different specific humidity it is mixed together, and then it is going, and then you can have a control, like you can give different values of flow rate, different values of specific humidity and whatever you can have, then you can control whatever it is having at the exit at the station 3, right. So what will happen? Like I need to analyze it. What I will do? I will take a control volume, something like that I can take. This is my control volume, right? And you can do this mass balance, energy balance and other things, right? Okay. And of course, you will have to use also this psychometric chart which I have shown here, like this is at station 1 and this is station 2. If you join this thing, and you will get in between, right? That is the station 3 you will be getting. And you can use this very easily and get the calculations and other things. So if you look at, we will be doing the mass conservation for the dry air, that is m dot A1 plus m dot A2 is equal to m dot A3, right. This is general one, which we have done several times. So similarly for the water balance, what we will do is basically MW1 plus MW, of course this will be G1 water vapor, right, G2 is equal to MW2, G3. And that we can express in terms of specific humidity, MWA1 SH1 plus M dot A2 into SS2 is equal to M dot A3 SS3, right. With this water vapor we can express in terms of the mass of air and their respective specific humidity. And if we can do this energy balance, we can get M dot A H1 plus M dot A2 into S2 plus M dot A3 into S3, right. So, we can get this balance. And from your this equation, if I say this is equation 1, right, from this equation, and I can use what you call mass balance here, M dot A3 is equal to M dot A1 plus M dot A2. Here I can put it here that M dot A1 plus M dot A2. That is exactly what I have written here. And then you just take what you call mass of air, separate it, and then you will get a relationship between mass of air at station 1 divided by the mass of air, mass flow rate of air at station 2 is equal to SS2 minus SS3 divided by SS3 minus HS4. So, if you look at, if I know this one, right, let us say I know the mass flow rate, I can very easily find out, this thing, what you call, like from here, that is the SS2, if you look at SS2 minus SS3, right, and if I can find out SS3, right, minus SS1, this portion, right, provided I know these values, right. Or if I know that what is my desired level, SS3 I know, SH1 this is known, right. And if I know this is, then I can find out what will be mass flow rate of air. From very happily you can find it out what it would be, right. One of them of course you should know, the rest of the things you can find out. You can tinker and find it out what it would be. So, this is a very simpler way of doing, and similarly we can think of doing this from this energy balance, that is equal to M dot A1 divided by M dot A2 is equal to S2 minus S3 divided by S3 minus H1, right. Of course, star is not being used, but I have used because I have introduced, and it is, you can use enthalpy. So, that also you can get from here that H3 minus H1 is here, because if I know this point what I want, and then similarly S2, S3, any one of them unknown you can find it out from here very easily, right. So, what we will do, we will basically looking at this like another example, that is evaporative cooling, right, which we use in our day-to-day life, particularly evaporative cooling is as old as Indian civilization, and the examples, if you look at pictures, even our human beings, animals, plants, all use the evaporative cooling to keep the body temperature and other things, right. That is why we sweat, like, and then that will be evaporated and our body will be maintaining its temperature. So, as I told that evaporative cooling is known to us for more than 3000 years, for which are used for cooling of drinking water, right. The examples you know very well, the pitcher, right, and pitchers are not being used nowadays, because there is not many people who can really make the pitcher. I am sorry to say this, because that is the state of the art. Because if you buy a pitcher from the market, it is not having porous. People have forgotten how to make the porous. How it does work? It will be having very, very tiny pores will be there, right? And through the pores, right, through these pores, that water will be coming out. Of course, depending if humidity is not much, like a little dry is there, and then that will be evaporated. But today you will get the pitcher, the pores are not there, they have forgotten how to make the pores. Therefore, you are not getting very cool water, right? Okay, it's very unfortunate. We lost that technology which was there for us for 3,000 or maybe 5,000 years back, but we lost in the process of modernity. Right. And we use this thing also in our coolers, which we call, air cooler, right? We call it, and this is known as desert cooler also, or swamp cooler, because what happens if it is dry, then dry, that means not much water vapor is there in your air, like your northern belt of the land, like Kanpur, New Delhi, Rajasthan, other places before the monsoon set in. This is a very beautiful system, which of course I use in my home and this cooler. And this is being devised by us, right? And what it does is basically sprays the water and the hot dry air enters into it. This you can model that way. These are the, water will be there here, it will be kind of things, and then air will be entering to that and it is sucked out. This is your, fan, exhaust fan, what we use, and then you will get the cooled air because of evaporation, right? And if you look at what is happening here, the process is basically enthalpy will be remaining constant and also the wet bulb temperature remaining constant. But if you go beyond it, then water will be very thin and it will be moist, is not good. So therefore people try to, these things. So therefore designing of that also is very important. What surface area will give, what are the things, how much you can close, or such that it can really keep the temperature lower. So if you look at your earlier here, TdB1, and this has been reduced, TdB2. So if it is less than the TdB1, so you are getting the lower in temperature. So that is the thing what one can think of using, we use it, and analysis will be similar in nature. So another examples I would like to give, that is known as the cooling tower, which we use for the power plants and large air conditioning system and refrigeration system, large industries, right? Because we use a lot of, particularly in industries, large quantity of wastewater. Wastewater means heated water basically, and then that can be cooled down very easily, right? And if you look at, in our campus itself, there was a cooling pond, which you might have seen. It is in a dilapidated condition at this moment. That is located in front of what? Library, central library, right? And that is a pond which was being used for air conditioning our library earlier days, but now they have replaced. And that is a beautiful system. And it is also beautify our camp, places. Earlier there was a fountain and you do that. So typical cooling tower looks like this. Like if you look at, there is a water, warm water enters over here, right, which produce the spray. That means water will be sprinkled, put into droplets, surface area will increase, so that evaporation will be, enhanced. And then there is a fan which is being used, right? And this fan will suck the air and will take the air also here, and this water which will be sprayed down and will be coming over and collected here, and at evaporation is taking place, some of the water will be going through this, this is some of the moist air, right, which will be going through that because it is evaporated and going through. As a result, what will happen, the water whichever is this thing, there will be lower, that means less amount of water will be collected here than whatever is going through. And that water, difference, we call it as a makeup water, like because the difference will be there due to the evaporation, some of the water vapor will be converted into its vapor and carried away by the air. This is where you will have to give some power, like it is some soft power you will have to give, you will have to use some energy for that. But there is another way. This is where the spray will be there, it is having same collected, but this is a what you call chamber which is given such that, it will be take the air naturally. It is a very long, I have shown it very less, but actually it is a very long tower. This is known as the kind of things, and this is known as natural, right, cooling tower. It's like a chimney, like you might have seen for our here in Kanpur area, like you are having lot of brick industries. The chimney will be there, tall kind of thing, and this curvature, which is very important for the designing and how it will be taking care of that part. And here it is known as force cooling tower, right? Force convection, you can say, right, tower, because it is you are using the fan which will be taking away. Here there is no energy is required, it will be going automatically because the water vapor is lighter, isn't it? Because its molecular weight is much lower than the air. So therefore, once it is converted into vapor, it is very lighter and it will be carrying away this thing. So how we are going to analyze that? So as I told, this is force cooling tower, and then we can think of using basically two things. One is atmospheric air is entering, right? Okay, and the wet air going out, and spraying water is coming, which is warm or the very higher temperature, right? If you can think of this is T3, right? And this cooling water is going out at the end. There will be collected here and is going out. This we are trying to model basically, and this T4. So T4 is less than T3 always. Otherwise, what is the purpose? Okay. So therefore, if you look at what we will do, we will do the mass balance for the dry air, that is mass flow rate of air at station 1 is equal to mass flow rate of air at station 2 is equal to mass flow rate of air, right? And we will do the water vapor, right? And this is, if you look at this portion, is nothing but your MWG1, and if you look at this is coming with the atmospheric air which is entering into tower, plus the amount of spray water which is coming, MW3, simple water, nothing else, okay? This is a warm water, is equal to MWA2 into SS2. So this is the amount of water vapor going out at this point, right? This is your MWZ2, right? And this is your MWG1, MWA1, right? Plus this will be total, right? Total air is coming. So MW3, which is MW4, which is the cooling water, right? This is a cooling water. So what you do, you basically you can say that this is MW3 minus MW4 is nothing but mass flow rate of air, because by mass balance, right, we know that, into SS2 minus SS1, and this is known as the makeup water, right? That means this is the difference, the MW3 minus MW4, what is that difference? That is the amount of air which goes out of this cooling tower, through the station 2, right? So, and we can do energy balance, like that is the enthalpy at the station 1 here, right, and into the enthalpy which is entering into the cooling tower, right, to the spray bar, what we are using is equal to the enthalpy is going out at the exit from this, and the enthalpy of the cold water. This is your enthalpy of the cold water which is going cooling tower, right, going from the cooling tower. So if you do that, then you will get basically I can take this out, MW3S3, that is your this term, minus MW4H4 is equal to MW is equal to M dot A2S2 minus M dot A1H1, and of course M dot A2 is equal to M dot A1 is equal to M dot A. So therefore there is a change in enthalpy, right? You can take out. So, in this case what we are doing, in place of your MW4, I can use this expression, that is MW4 is equal to MW3 minus MWA SH2 minus HS1, and I can use this expression over here, right. I can use this expression over here, and then I can get this expression that is given, like m dot W3 S3 minus, this is the bracket, like for the mass flow rate of water at the station 4 into enthalpy at station 4 is equal to change in enthalpy between the station 1 and station 2. So, I can find out the amount of mass flow rate of air which is entering into the cooling tower is equal to MW3 into S3 minus H4 divided by S2 star minus H1 minus in the bracket SS2 minus SH1 into H4. So, this way we can calculate the amount of this thing, we can use this expression, right. So, I can take an example, right, just to solve a problem, that in the thermal power plant a cooling tower is used to provide cold water at temperature 25 degrees Celsius to the condenser, right. And this cooling tower receives 1200 kg per second of warm water at 40 degrees Celsius and the atmosphere at 45 degrees with RH of relative humidity of 0.2 enters into the tower and leaves it with a 45 degrees Celsius, right, with relative humidity of 0.7, and we need to find out makeup water, right, and air flow rate. So, if you look at what are the things are given here, see, if you look at like your T1 is given, T1 is 45 degrees Celsius, right, and RH 1 is 0.2, and this thing is leaving, the cooling tower receives 120 kg of water, right. These are the 3. This is your basically MW3 is 1200 kg per second, and this is at 40 degrees Celsius, right. And we need to find out, basically MW3, right. This is the station 3, right, minus MW4, and I will have to find out mass of air, how much air is entering. So, what we will have to do? We will have to basically, we can use the psychometric chart, right. From psychometric chart, we can get corresponding to 45 degrees Celsius, right, and RH 0.2. So, we can get very easily, that is RH1 is 0.2 and T1 is 45 degrees Celsius. I can guess SH1 is 12.25 gram per water per kg dry air, right. And we can also get from the same psychometric chart we can get the TDB, that is dry bulb temperature 35, this would be 35 degrees Celsius, okay, 35 degrees Celsius. This is not 45, this is 35 degrees Celsius, and RH is equal to 0.7. So, I will get SH2 is 0.027 kg of water into kg of dry air. Okay, H2 I can get 105 kilojoule per kg. Okay, and these are the data we need, and H1 we can also find out from psychometric chart, that is H1 is equal to 80 kilojoule per kg. Okay, and from steam table at 40 degrees Celsius I can get PWS is equal to 7.384 kilopascal, HF 1674.54 kilojoule per kg, and which is nothing but your H, what you call 3, right? This is the station 3, right? And at 25 degrees Celsius, right, cold water, PWS is equal to 3.169 kilopascal, HF 104.87 kilojoule per kg, and which is nothing but your H4. Yes, H4, right. And so what we'll have to do, we'll have to basically do this energy balance and then mass balance, and then we'll calculate, because we know all those data, right. And by mass balance for water, we can get MW3 plus MWA SH1, that is entering 1 and 3 entering, is equal to MW4 plus MA2 SS2. So if you look at what is MW3, MW3 is nothing but here given 1200 plus M dot A, and SH1 is given 0.01225. I am using kg per of water per kg of dry air, is equal to MW4 plus MWA into 0.027, that is SS2, right. So you can use this equation 1, and by energy balance, I can get basically MW3 S3 plus MWA H1 is equal to MWA S2 plus MW3 H4. So from this I can get basically MW3, right, H3 minus MW4 H4 is equal to MWA S2 minus H1, and we know this thing, H1 is known, S2 is known, and we do not know MA, but MW3 is known and MW4 is not known. So we can write down here like that 1200 into H3 is known, that is into 167.54 minus MW4 into, this is known, H4 is known, so 104.87 is equal to what you call M dot A into 185 minus 80. This already we have known from the psychometric chart, we know this thing. So you will get equation 2 here. So if you look at this, if you do that, solve this thing, equation 1 and equation 2, and eliminate this mass flow rate of air, I can get MW4 is equal to basically 1152.96 kg per second, right. Okay, so if you look at what is the makeup water is MW3 minus MW4. What is MW3? 1200 minus 1152.96, which is giving me 47.04 kg per second. If I use this, in equation by using equation 1, because I know this MW4, so I can find out M dot A is equal to 3189.15 kg per second I can get. It is very easy actually. If you look at what you can do, you can get from here, right, that is from equation 1, I can get MA 0.027 minus 0.01225, right, is equal to 100 minus what you call, that is the MW4 is 1152.96. So therefore we can get from here, right, very easily, and then that is 3189 per kg per second very easily, right. So if you look at by this way, you can solve how much air is entering into this cooling tower, and what is the makeup water one has to provide, like kind of things. So by this way you can do. In this case, what we have used? We have used both the psychometric chart, and we have used the steam table for the data, saturated steam table, and you can also do a little hand calculation to be, it will be a little slower, like that I can do. So with this we will, we have completed the what you call the psychometric or the air conditioning part, and next class we will be discussing about a new topic which is known as thermodynamic relationship. Thank you very much.